give you a quick review for previous class. In lecture 5, we are going to discuss the diffusion in materials with crystal imperfection size. For example, like polycrystalline materials. Inside these polycrystalline materials, we have two-dimensional crystal imperfection size grain boundary, and now we have this kind of materials. So what is the divisibility, or how's the atoms diffuse in these polycrystalline materials with grain and grain boundary? And in lecture 4, actually, if we deal with single crystalline materials, included the metals and ionic materials, and you can easily formulate the divisibility equals to total jump rate, mean square jump distance divided by 6 times the correlation factor F. And based on different types or kinds of diffusion mechanism, you can easily obtain the divisibility, the expression of a divisibility in single crystalline materials or ionic materials. But now what we deal with, or what we have, is polycrystalline materials. So now you need to consider what the diffusing atoms not only diffuse inside the grain, also have chance to jump into the grain boundary and diffuse through the grain boundary, and also probably also jump in the other grain and diffuse into grain again. So how to obtain or estimate the divisibility of this kind of material? And this kind of divisibility, we sum all the possible diffusion paths, included the diffusion in the grain and also in the grain boundary. The sum of this, contribution, or some of the contribution from different diffusion paths, we call it as effective divisibility. You need to consider the volume fraction of the grain and also the grain boundary into these materials. Okay, so this we call effective divisibility, and we can measure this from your material. Okay, because it is a sum of the divisibility from different diffusion paths. Okay, so in previous class, we also mentioned about the atoms diffuse through grain boundary and diffuse inside the grain. Which one is much easier, or which divisibility is higher? So based on the energy as a function of location, and the green curves represent the atom. If the atom at or inside the lattice, it need to overcome this energy barrier or activation energy, then they can allow these atoms jump from this location to this location. But if now we have an atom located at grain boundary, and grain boundary usually have a higher energy than that in the lattice, so the energy barrier which the atoms need to overcome is smaller than the atoms at the lattice, inside the lattice. So in other words, that the atom at the grain boundary can diffuse faster than that inside the grain. So the divisibility of the grain boundary is larger, usually is much larger than the divisibility inside the lattice or inside the grain. So this slide is going to show you how we you can measure the effective divisibility of your material, right? It's measurable, but if you want to, if you are interested in the contribution from different diffusion paths, how to estimate or how to calculate to get the effective divisibility. As we mentioned, you need to, first of all, you need to make a very important assumption is the dxlt will be larger than s squared. This means that the diffusion length is larger than a diameter of a grain. This tell you that what? This tell you that you cannot ignore the divisibility inside a grain is fast. You cannot ignore it. And based on this assumption, then we need to calculate the fraction of the time to the diffusing atom spent in grain boundary versus in grain. So now we know the ratio, and this ratio must proportion to the available jump site and also proportion to the volume of fractional volume of the grain boundary versus the grain. So based on this concept, we can get that this is a volume fraction of the grain boundary divided by volume fraction of the grain. So you got this ratio. So we take this result in here, and we can get that the mean square, the total mean square displacement effective divisibility times d will be contribute from two parts. The first part is contribute from diffusion or displacement inside the grain. So it's a divisibility times t, and the fraction is 1 minus iota, and plus the divisibility along the grain boundary, and the total diffusion times t, and we put the iota. Iota t is the real time, and your real time to the diffusing atom really stay into the grain boundary. So we drop the t out, then we can get the divisibility express. The effective divisibility is expressed like this. And some people usually will ask, yes, although I have a polycrystalline materials, can I just simplify? We don't need to consider the contribution from the grain boundary. Can we do that to simplify the questions? The answer probably would be you need to do some estimation. What kind of estimation? What kind of estimation you need to perform before? First is you need to estimate what's the delta. Is you need to use the TM to measure the thickness of the grain boundary and also the size of a grain. Based on this example, we know this portion is 1/1000, right? So if the dB is faster than dxl by 3 orders, then you cannot ignore this term. You need to take this term into account, right? You need to consider this term. So it's easy to you to have some idea whether you can ignore the diffusion contribute from grain boundary or not. You just need to have this kind of estimation, then you have idea. But sometimes, yes, effective divisibility is contribute from different types or kinds of diffusion path. For example, like from the grain boundary. And if you have free surface, probably you need to end the free surface part and also the dislocation part. You can end lots of possible diffusion path exist in your materials. Yes. But at my interesting temperature regime, we want to know which diffusion path is dominant. Is a dominant path for the specific for specific temperature or in between the interesting working temperature. Then you can do one thing is you can just you can just measure the effective divisibility of your material at different temperature and plot the log effective divisibility over versus 1/T. And if you see the one straight slope, that means doing in between your interest during this temperature region, only one diffusion is only straight line like this, and only one diffusion path dominates this diffusion of the diffusing atoms. But however, if you got the data, you got is a curve and can be fitted into two straight lines. That means what? During your interesting temperature region, there are two possible dominant diffusion paths. And based on the slope, because you know the slope, right? And the slope is corresponding to delta H over K. So you can simply get the energy term. And based on the energy, you can guess or you can estimate what kind of diffusion mechanism dominate in this region and also in this region. Okay? Okay. So this is the way you have chance to know more about the diffusion mechanism involved in your materials. And as we mentioned, based on now you have a grand boundary is a possible diffusion path, right? So there are three different regions of grand boundary diffusion in polycrystalline materials. And within time t, in the beginning you can observe the diffusion source on the top of your material, and this is a cross-section view. So the diffusing agent diffuse along this direction. And after time t, diffusion happens, and after time t, you can observe different types of diffusion patterns. And the first one we call A region. The diffusing agent diffuses through all materials. And this we also call it as a multiple boundary diffusion region. And the characteristic for this case is the diffusion length inside the grain is much larger than a size of a grain, a diameter of a grain. And the region B is totally okay. So the region B, actually the pattern is totally different with region A, right? The pattern is turns out that the diffusing agent diffuses through the grand boundary, and also the diffusing agent also jump in the grain and diffuse into the grain. So you can observe this gray region, thicker region in this boundary region, and this we call it the intermediate region. And the characteristic for this region is diffusion length along the grain boundary is larger than a diameter of a grain, and the diffusion length inside the grain is smaller than S, but larger than lambda. Lambda is interatomic distance, is in the angstrom order. And for the region C, actually is you didn't see this thicker line, gray line, right? So this means that diffusing atoms diffuse only through the grain boundary. And yes, the atom jump into the grain, but the diffusion length inside the grain is very, very small. You can ignore that. So you only see this kind of diffusion pattern. We call it as a C region or core-only region or boundary-only region. Okay, so based on the, if you want to write the characteristic of this region C down, then would be the diffusion along the grain boundary is larger than S, and S is much larger than interatomic distance lambda, and diffusion distance inside the grain is smaller than lambda. Okay, so you can have some pictures or idea about by the difference between the DXL and DB, then we can get different kinds of diffusion patterns for grain boundary diffusion, right? Okay. So as we mentioned, and by the way, the region B and region C, some people also call it as an isolated boundary diffusion region. And that means that the diffusion mainly focus along the grand boundary. And also, if you consider the concentration of diffusing atom inside the specific grain, you only need to, when you want to calculate or estimate the concentration of diffusing atoms, you only need to consider only one diffusion source. So we call it kind of isolated boundary diffusion region. You don't need to consider different sources. Okay, just one source, so we call it isolated diffusion region. And region B is more, you need to put more efforts here. The difference between region B and C will be this one. The diffusion length inside the grain is smaller than S, and this one is smaller than lambda. Okay, so you can observe, yes, in this region B, the diffusing atom did diffuse inside the grain. But in this region, the diffusing atoms did not, or only diffuse few into the grain. Okay, and both these cases we assume is a stationary boundary, means the grain boundary doesn't move during the diffusion process. It's a stationary boundary. But however, as you know, when the grain growth or recrystallization happens, usually our grain boundary moves during both of this process, right? So now here we need to consider if we have a non-stationary moving grain boundary, then can we also easily to classify or divided all the diffusion patterns into 3 different cases? How to do that? So the textbook gives us a simple way to do that. The vertical axis is a log dxlt, is a log diffusion length square. So it is a dxlt. And the horizontal axis is a log vt, is the moving distance of the grain boundary. Vt, because v is a moving velocity of the grain boundary, and t is a diffusion time. So Vt is a moving distance of the grain boundary, and this is a diffusion length of the diffusing atom inside the grain, and square it. Okay, and next you need to take a look on this marker. We also mark some point for the moving boundary. The Vt part, the lambda means the log lambda means lambda is in the angstrom order, right? And log s is the diameter of a grain, and the vertical part actually is s square and lambda square. Okay, so as you know, square root of dxlt compared with s is the indicator how we determine whether the diffusion pattern belongs to A or B, right? So as you know, if the square root of dxlt much larger than s, then we will say this diffusion pattern will belong to multiple diffusion pattern. There's like the pattern will be like diffused through all material, right? So when you square this term, this equation, then you got s squared smaller than dxlt. This is a region here, right? The dxl much larger than s squared. So this region definitely is a multiple boundary diffusion region, right? Okay, and next, in order before we talk the detail inside these figures, I want to point out one important thing is this is log s squared, and this is log s. Even you look like the distance the length are similar, are same, right? The lengths are same, but s squared actually is much larger than s, right? So the scale for vertical axis is different with that in horizontal axis. The scale is a little bit different, okay? Next, we are going to focus on the VT. VT is the moving distance of the grand boundary. So if a VT is smaller than lambda, that implying that what? The moving distance is smaller than several angstrom. That implying that this region is a stationary grand boundary. So if the VT is smaller than lambda, this region belongs to stationary grand boundary region. This is what we mentioned in previous slide, right? Stationary boundary region. So based on this is stationary boundary region, and based on different dxlt versus s squared and lambda squared, then we can classify into 3 different types of diffusion patterns. If the diffusion distance much larger than s, then belongs to a multiple boundary regions diffused through whole materials, right? And if the diffusion length square root of dxlt is smaller than s, larger than lambda, then belongs to B, is the boundary region or intermediate region, right? Is smaller than s but larger than lambda. That means the diffusing atom diffuse inside the grain, but the distance is not still smaller than s. And region C is what? The diffusion distance is smaller than lambda. That means what? The diffusion only happens in where the diffusion into the grain is very, very small, tiny small. You can ignore that. So it's a region C, right? Is a lambda larger than diffusion distance inside the grain. Okay, so ABC is what we discussed, is ABC. Okay, so this portion belongs to stationary grain boundary, and this portion definitely belongs to moving grain boundary. And we deal with this one. If the VT is larger than S, what does this mean? That means the moving distance of the grain boundary is larger than S. So for example, like this case, if the VT is larger than S, that means if we have a grain 1, 2, 3, and this is a grain 2, right? And this is a size of a grain S, and there's a grain boundary between 1 and 2. What means the VT larger than S? Means this boundary moves larger than S. So you can expect the diffusion patterns must what? Multiple boundary region is like the region A is diffused through whole materials, right? And what about if the diffusion distance plus VT, the moving distance of the grain boundary, is smaller than S? Smaller than S, that means this grain boundary just moves tiny, smaller than S, right? And this kind of pattern you can expect actually definitely is isolated boundary diffusion. It's either B or C, right? It's either the boundary region or core region. If it doesn't diffuse into the grain, we call it core region. But if it diffuses inside the grain, then we call it a boundary region, depending on the value of a magnitude of the diffusion distance, dxlt, right? Okay, so we finished this part. This is multiple, and this region you can, based on the magnitude of dxlt, you can separate them into. If dxlt is larger, that means that the diffusion into a grain is the diffusing agent diffuse into the grain. So this is a moving boundary, isolated boundary, and also the crystal diffusion penetration. Because this region, the d-axis is larger than this region. This region, the d-axis is smaller, right? And in this region actually is what? Because d-axis is smaller, so that implies that there's no crystal diffusion penetration. It's similar to the core region below with a moving boundary. Okay. Okay, so next slide. Some people probably will ask, yes, Yin, I have a question, or Professor, I have a question. In the stationary boundary region, the border between region B and C is a horizontal line. But why in this moving boundary cases, the border between the penetration and non-penetration would be this with this kind of slope, the line with this kind of slope. And what's this kind of slope? Why can we derive or prove this one? And what's the slope of this straight border line? Yes, this next slide is going to explain and help you and tell you how to get or calculate this straight line with a slope, this one. So now we are going to give you an example to explain this. So in order to prove this border line, first of all, you need to assume a case will be with a moving boundary. So now we have a ground 1 and ground 2, and in between is a ground boundary. And it's a moving boundary, so we assume the moving velocity is v, direction is toward to right-handed side. And some people probably will ask why the ground boundary moves. So the reason is here. The diffusing atoms diffuse through the ground boundary, and some atoms will jump to the left-handed side, and some will jump to right-handed side. As long as the numbers of atoms more atoms jump to left-handed side, they will push the ground boundary toward to right-handed side with velocity v. So this is why you observe the moving ground boundary. And in this case, we try to plot the concentration of diffusing atom as a location x. And before diffusion happens, and the coordinate will be t equals to 0. The coordinate will be located here. But after diffusion happens, for example, like after time t0, you can observe because the boundary moves right along with velocity v. So the coordinate moves to here, right? And in the meantime, the diffusing atoms at ground boundary diffuse into the ground. So this is a ground 2, right? Ground 1 and ground 2. So this case happen two things. The first thing is the boundary moves with velocity v from here to here. And the second thing happens simultaneously. Happens in the meantime is the diffusing atoms with C0, concentration C0 diffuse into the ground. Okay, so based on this kind of situation, we assume that now is in the quasi-steady state. That means the concentration profile does not change with time, and v equals to constant, the moving velocity equals to constant, and the flux of the atom, diffusing atom into the forward ground can be formulated based on the fixed first law will be minus divisibility dxl concentration gradient. It turns out it's correct, right? But however, the coordinate moves from here to here. So this region, the numbers or the flux of the two inside this region is not really passing through this plane. It's just because the moving boundary. So we need to minus this extra flux to modify, to get the modified flux, which is really passing or flux in to the forward grain. So because we also assume it's quincy steady state, so the flux should be equals to constant. So this region, this flux equals to constant. So this will be constant. So as long as this constant, you can solve the C as a function of X location. Then you find, based on these results, we know the concentration profile within the grain, this is grain, will be obey the exponential decay at X equals to 0. The concentration will be C0 and obey this exponential decay. And what I'm interested in is, can you just have some idea about the exponential curves? Yes. We can divide it by V together. So the upper portion, we got the minus X, and the bottom portion, we got the dxl over V. And we assume we let this as equals to lambda is the interatomic distance. So while the X equals to lambda, then at that location, at X equals to lambda, at this location, the concentration becomes to E minus 1 of initial concentration, will be C0 exponential minus 1, right? So this is lambda is very important. Why? Because you can expect if this is this lambda, if this is a at this lambda location lambda, the concentration becomes to E minus 1 of C0, right? And if lambda is very small, that implying what? Lambda is very small. This lambda, right? If lambda is very small, that means what? The diffusing atom did not diffuse as deeper as it. So it's just diffused slightly into the grain. But if the lambda is very large, like this large, and also lambda, so the lambda here is larger, right? Lambda prime. That means the profile tell you that this diffusing atom diffuse into the grain and even diffuse more or diffuse deeper into the grain. So this is slightly, so this pattern is similar to coal, right? And this one probably is similar to boundary regime B. And this part 1, if the lambda approach to infinity, then it's similar to what? Is similar to pattern A, right? Diffuse along through whole materials. So the lambda is quite important because at this location, this location is with concentration becomes to E minus 1 of original concentration of diffusing atom at grain boundary. Okay, next yes, now you have idea about what's a lambda, right? But the purpose here actually is demonstrate the straight line, the slope of that straight line. So because we sent this as a lambda, so we move V to right-handed side and times the T together. So we will got this, and we take a log on both sides. So we got the log dxlt, log Vt plus log lambda. And here, if you consider this as a vertical axis, this is a horizontal axis, then the slope becomes to 1. So this is what we have here, right? This is log dxl, this is log Vt, the slope is equals to 1, okay? And as we mentioned, yes, now you have the borderline. So if the dxlt is larger than Vt, dxlt is the diffusion distance is longer or larger than Vt, the moving distance of the boundary. Diffuse dxlt is larger, then that tell you that the diffusing atom diffuse inside the grain. So we call it XL, or the crystal diffusion penetration. On the contrary, if the XL is smaller than Vt, then smaller, very small lambda, then is a non-crystal penetration. So now you have some idea. Yes. If the diffusion is the XLT larger than S squared, or the VT is larger than S, then this belongs to multiple, and this region belongs to stationary, and this region is we consider as isolated, right? But inside isolated, depending on the magnitude of the XLT, this one with higher the XLT diffusion distance or length, so also can be considered as penetration, diffusion penetration part, crystal diffusion penetration. And this one region with the smaller the XLT, you consider no crystal diffusion penetration. Now I believe you have some pictures or idea about these figures. Okay. So now we need to now you have the stationary or moving grand boundary, and based on different XLT, then you got a different diffusion patterns, right? But the purpose to learn these different diffusion patterns is based on we want to solve the concentration profile or concentration of diffusing atom at inside the grain. We need to know, or we need to obtain the concentration in the grain. But if your case belongs to A region, that means the diffusing agent diffuses through whole material. Then if I'm interested at this location with X, Y, and at T, then you can simply get this based on the what you learn in lecture 3 is based on the first of all, you need to determine it is a limited source or unlimited source. And as long as you know the X, Y, the location, exactly location, then you can use the corresponding solutions for limited source or the unlimited source. Then you can get the concentration profile, concentration as a function of location and time. So this is easy, right? This case, you just use the what you learn in lecture 3. So here we just introduce the region B will be more complicated, because if you want to know the concentration inside this grain at this location inside this grain, you first of all you need to consider that because the atoms diffuse through grain boundary, then slightly diffuse into the grain inside the grain. So you need to sum all the possible diffusion. All the possible diffusing atoms through different diffusion paths, included through the grain boundary and also through inside the grain, right? So just a quick review, intermediate region is the characteristic here is the diffusion distance through the grain boundary is larger than S, and S is larger than diffusion distance inside the grain, and this is larger than lambda. So here we are going to introduce a method which we call a Fisher's analysis to obtain the concentration profile as a function of location and time in region B. Okay, so how to do that? So first of all, we give you pictures here. This is also a cross-section of your materials, and we have a diffusion source on the top of these materials, and now we have a grain 1 and grain 2. In between is a grain boundary, and because the diffusion source is on the top of these materials, so you can expect it. If I ask you the concentration of diffusing atom inside the grain at this location inside the grain, you probably will say, oh, the concentration should contribute from where? From either this location diffuse from this or from this, right? From here, directly from the diffusion source, or through the grain boundary, then diffuse into the grain inside the grain, right? So yes, as you expected, if you take a look on this grain, we believe because the diffusion source is on the top of it, and as you know, the grain boundary dB must be larger than dxl. So diffusing atoms will be, some diffusing atoms will diffuse here and get into the grain. So you need to consider the contribution from the top of the source and also from the grain boundary part. So inside this grain, this portion will be with higher concentration of diffusing atoms, and along this direction, the concentration will decrease along this direction. So this is the contour of a concentration profile, means that each location has a same concentration of the diffusing atom, and the same idea can be applied on grain 1. This region with a higher concentration of diffusing atoms and decrease along these directions, and also have a contour of concentration profile. And so in order to get the concentration of diffusing atom as a function of location and time inside the grain, so we need to formulate the diffusion equation. And this will belongs to two-dimensional diffusion equation, right? Because it will belongs to two-dimensional from the top and also from the grain boundary. So the partial C, partial T will be minus flux divergence, but the flux will be separate. Or you need to consider along x and y axis from the y and x axis. And we based on this diffusion equation, we need to formulate the grain inside the grain, the diffusion equation inside the grain and also on the grain, in the grain boundary. So first of all, we need to assume the diffusivity inside the grain or inside the lattice is equals to constant. So we can take this diffusivity out, and we will get the diffusion equation inside grain 1 and 2, right? The diffusivity concentration gradient obeys fixed first law. And how about how to formulate the diffusion equation in grain boundary? Yes, we just concentration profile as a function of time, concentration gradient, and here because we put more the concentration here is on the boundary, so we use the B to point out the concentration we talk about is a grain boundary, and diffusivity concentration gradient and only along y-axis, so we don't have the x-axis part because we only have this. The grain boundary is just along y-axis. But don't forget the diffusing atoms will either jump into a grain 1 or jump into a grain 2, right? Not just go straight along the grain boundary. The diffusing atoms can jump left-handed side or right-handed side along the grain boundary. So you need to minus the flux concentration gradient. And this one is like the flux I just mentioned. The atoms have chance to jump into the grains, including grain 1 or grain 2. So it's a delta Jx, the direction is Jx, right, along x-axis. And based on this, the flux is obey minus diffusivity concentration gradient, and the diffusivity will be the diffusivity inside the grain, dxl. And concentration gradient will be, because jump in, so will be at this location. So concentration gradient at x equals to delta over 2. And the flux go into the grain 2 will be the same with that go into the grain 1. So we use the 2 times the flux part. And also the delta x actually is the thickness of this grain boundary, so we use the delta. So we use this to substitute this term. So in order to simplify both this equation, so we then x1, y1, and t1 as like this respectively, and this actually is dimensionless because x is in length divided by length, so it's a dimensional list. So after we use the x1, y1, and t1 to substitute this equation, we just write, then we can get the new diffusion equation in Green and also in Green boundary expressed in x1, t1, and y1. And in order to solve these diffusion equations, what you need to do is you need to write down the initial and boundary conditions in this regime B or in these diffusion cases. So initial boundary condition means t equals to 0. So before diffusion happens, the CB at 1 x1 equals to 1 over 2, and also x1 equals to minus 1 over 2. The CB, the concentration of diffusing atom at CB would be equals to 0 because the diffusion happens. And this is the other boundary condition. At any time point during diffusion, this point CB at y equals to 1, y1 equals to 0, CB at y1 equals to 0, the concentration must equals to 1. The 1 actually means the constant. We use the 1 to substitute the concentration of diffusion source. But for example, if your diffusion source is 2% or 3%, you can just use the 2% or 3% to substitute this 1. Okay, we just simplify that, so we give you 1 to represent the CB, the concentration of CB. Okay, so now you have initial and boundary conditions. So first of all, we need to deal with the Green diffusion equation inside the Green. So inside the Green, we just copy the diffusion equation, two-dimensional diffusion equation. In order to simplify this two-dimensional diffusion equation, you can think about one thing. If we are interested at the concentration inside this Green, this location inside the Green, and as you know, the GB diffusion along Green boundary is much faster than that in the lattice inside the Green. So you can think about if at this location, you can consider what the diffusing atom mainly come from Green boundary because this is fast, right? And fast and severe diffusion source and diffuse into this location. But this one is very slow, right? So contribution along y-axis is quite small, so you can ignore this. So it becomes to diffusion equation you're familiar with one parameter, x1. Okay, so diffusion into the y-axis can be ignored because the d-axis is smaller, much smaller than dB. So the diffusing atoms mainly diffuse through Green boundary and diffuse inside the Green. Okay. Okay, so in order to solve this diffusion equation, you also need some initial and boundary conditions. For example, like before diffusion happens, the concentration, any location x1 and y1, the C will be equals to 0. So this is initial boundary condition. And also the other boundary condition will be at this location, the C at 1 over 2 or negative 1 over 2 will be equals to C belongs to concentration inside the Green, right? At this location, the C will be equals to CB at same location at any time point. This concentration at this location, CB will be equals to C, right? Okay, so if I'm interested in the concentration at this location, so you can consider this is a surface concentration. This concentration of diffusing atom serving as a diffusion source diffuse into this Green, right? this location, right, contribute to this the concentration on this location. So this you can consider as what you learn in lecture 3 is constant surface concentration cases, because this concentration does not change with time, right? At any time point, it always equals to Cb, right? And serving a diffusion source, and the case will be constant surface concentration cases. And don't forget, the diffusion along grain boundary actually is what you understand or you know is the diffusion source diffuse through grain boundary, so this region with higher concentration and decrease along this direction. But you can consider, yes, this is higher, and this is the concentration is higher, and gradually decrease the concentration of diffusing atoms. But to this location, the diffusion source is mainly come from this concentration at the grain boundary. Okay, but this concentration does change with Y and T. Okay, so I just give you a quick review for chapter 3. CS serving this is a surface concentration fixed diffusion cases, so we can get the concentration profile as a location and time, and will be expressed like this. And C0 means that the concentration of diffusing atom inside the grain before diffusion. So based on this, we just copy the corresponding solutions here, and based on this case, before diffusion, T equals to 0, we don't have any concentration of diffusing atoms, so we can drop this term out. And we can copy the corresponding result here. CS, you can take it out in 1 minus arrow function. And CS, in the cases we talk about in chapter 3, is a constant. Based on what is a constant, remain constant, right? But in this case, it is not a constant. The Cb changes with Y and T. So we use this Cb changes with Y and T, substitute CS, and the rest of part we just copy it 1 minus arrow function. And this x dt, we use the x1, y1, t1 to substitute it, then we will become this result. We can get these results. So based on these results, the only one term we don't know is the Cb. How the Cb, concentration of diffusing atoms in the grain boundary, changes with y1 and t1. As long as we got these results, then we can complete these solutions, right? So how to get this Cb? So we still have the other diffusion equation in grain boundary haven't been used. So this is a diffusion equation. We just formulate that, and we assume this is the quincy steady state. That means the Cb does not change with time. This equals to 0, so this equals to 0, so this will be equals to 0. Okay, then we are going to use this to get the Cb. The way is, as we know, partial C partial x1 as x1 equals to 1 over 2. We can just directly use the equation we derived in previous slide. This one partial with x1. You just need to partial this term. And at x1 equals to 1 over 2, then you can get this result. Then we substitute into this equation. Then we can get the Cb expressed like this. And this is only one unknown parameter. So we use one. We need to use one boundary condition would be at any time point, while y1 equals to 0 at this location, Cb equals to 1. So based on this, y1 equals to 0. This is 0. So this is 1, right? And this becomes 1. So a equals to 1. So we get so this is Cb. How the Cb changes with y and t. and it obeys exponential decay. You can expect it based on these results, and we substitute the CB term here. We successfully get the concentration of diffusing atoms changed with location and time, expressed like this. This is a CB, and also we use a 1 minus arrow function terms. And if you check your textbook, actually it de-emphasizes one criteria which you can use these results is, we just before from previous slide, the criteria would be what? The dB must be larger than dxl or something like that. But in order to quantitatively tell you how to in what kind of situation we can use these results, so the textbook gives you this kind of relationship. As long as the beta larger than 20, which is the delta dB over dxl square root of dxlt larger or equals to 20, under this situation you can directly use this result to obtain how the concentration profile change with location and time in region B. So I just directly use these results and put these results into Excel and try to give you more detailed pictures about how this diffusion patterns looks like. So this is the grain 1, and grain 2 is on your right-handed side. In between is a grain boundary. And on the top of this material, you got the diffusion source on it. So first of all, I just want to try to plot the CB as a function of y1 and time. So use this one. You just put in, and you can get the vertical axis is a concentration of diffusing atoms, diffusion sources, and the y1 is along this one. So you can observe this is exponential decay. Yes, it's exponential decay. And with increasing time from 1, 2, and 3, you can say 1, 2, 3, and even approach to infinity. Then you can observe the concentration profile very slightly increase. And this is tiny increase, so it can be considered as a consistent steady state because the increase is very tiny, right? So the assumption we just made is consider the diffusion profile CB does not change with time. Actually, it looks real because the reason for this one is that dB is quite large. Diffusivity along the grain boundary is quite large compared to diffusivity inside the grain. And this is exponential decay along the grain boundary. And if we take a look on this location y1 equals to 1, and as you know, this concentration will be served as a diffusion source, and diffusing atoms will be diffused inside the grain. So how the plot profile looks like? It will look like this is a C at different x1, and you can observe t equals to 1, 2, and 3. You can observe the increasing of the concentration of diffusion sources, diffusing atoms inside the grain. So this is how it looks like. But you can observe, yes, there's a 1, 2, 3, right? So the concentration increase larger and higher than that happens in the grain boundary. So, okay. So this we finish. Just show you. Hope you can have some pictures on the diffusion profile on the regime B. And additionally, some people probably will ask, Ying or Professor, how about at this location? Probably it's y1 equals to 3. And this concentration of diffusing atom will serve a diffusion source and diffuse into the grain. So if I plot here, this is smaller, concentration is smaller than here, right? So it will be like this. And also T1 equals 2 and 3. And so profile will be here. And if we take a look on y1 equals to here, y1 equals to 0.5, and this location will be serving a diffusion source, right? So it'll be like this, and like T1 equals to 1, T1 equals to 2, and T1 equals 3. So along this, along the grand boundary, the concentration is exponential decay, and at specific y1 serving a diffusion source diffuse inside the grain, so you can observe this kind of profile. Okay, so today ended here.